Good morning. Thank you everyone for joining us today on our Traction with Extraction, selection of DLE materials for lithium production. So today, this webinar is going to examine the different types of DLE materials to choose from and the decision process used when selecting a DLE material for use on brine. We would like to start off the webinar with a quick poll. So I will launch it. What we're trying to get here is, where do you stand in the DLE development process? Are you analyzing, oh, sorry, there's a typo, analyzing the brine? Are you in the process of selecting a DLE provider, or are you piloting the DLE? Thank you. So Grant should be on fairly shortly, and we will be able to get started. At the end of the webinar, there will be a Q&A, so please feel free to leave questions either throughout or just wait till the end. And whatever we do not get a chance to get to during the webinar, Grant will follow up in the upcoming weeks via email. We will also, the webinar is being recorded, so we will put the recording online on our website. I will also be putting it on LinkedIn, so you can find the link there. And Grant is always more than happy to share the presentation. So we should start fairly shortly. Oh, here we go. Grant, sorry, just your mic is off.
Sorry about that. Windows always wants to reboot your system at the most inopportune time. So.
Okay, well, Grant, I did the introduction. We've gone through the poll, so now the floor is yours.
Oh, excellent. Well, thank you very much, everyone, for joining us today. I thought this would be very, oh, there we are, a good opportunity in which to take a look at the direct lithium extraction materials. In working with people over the past couple of years now, I mean, that always comes up with the question is, of course, sourcing, doing exploration of the brines, but getting to the point to, okay, well, the next step is that, well, the direct lithium extraction materials, you know, who should I use and what should I select? So I thought it would an opportune time just to kind of review a very high level, as some of you that are already into the process can realize that there's a plethora of questions, and I'm going to say paths that you can go down. So this is meant as a very high level overview of the selection of DLE materials. The intent of this is just, I'm really going to take a look at two materials, which is going to be ion exchange and absorption materials. We will touch on the other technologies, but because of the time limits, I'm really going to focus in on really the main technologies that encompass probably the majority of the market share right now, or engagement. So with this, you know, absorption and ion exchange, I'm sure you're aware, is that the two basic, I shouldn't say versus, it's this or that. Absorption material, really, to give you a very generic description of this or definition, is that absorption materials is that the ions go onto the material and ion exchange materials go into the material. So that is a very crude analogy, but I think it captures the essence of the functionality of the materials. So absorption materials, it's lithium chloride that's absorbed and captured onto the surface of the material, and then ion exchange is going into the materials. So very easy, but it leads to a lot of complexity in the processes, as you're aware. So what I thought we'd take a look at, just as a deliverable, is just quickly, is the lithium market. Does DLE work? Types and methods of DLEs, the drivers, kind of the selection process, and getting into the characteristics of the material. This is not intended to tell you which material to select, but at least give you some framework or reference of the questions and the type of testings and the information that you should be gaining in which to make a knowledgeable and I'm going to say confident selection of the materials. So when we take a look at the DLE markets, sometimes I hear in the market space is that, oh, you know, DLE conventional technologies. Well, DLE uses conventional equipment in the process, but the DLE process itself is unique. And I'm going to term it as the Wild West right now. There's so many different process flow diagrams and so many methodologies and processes that can be applied to direct lithium extraction materials, as well as the direct lithium extraction process, that sometimes it's hard to keep up with. I'm pretty much engaged with probably about 40 plus projects around the world, and I'll tell you that there is a nuance or significant differences between each process flow sheet. But where I'm going with this, if we take a look at where we are in 1970 to now, you really see that really there's not a lot of people that, even though lithium production has been occurring, there's not a lot of people that were doing it. So Livent and I believe Sunresin were the only two people doing DLE, direct lithium extraction, using ion exchange adsorbents. But as the demand increased and outstripped the supply, more people have engaged and entered into the market space. So you can kind of see that it's kind of an open field right here, but as demand goes up, more and more people are starting to engage. And where we are right now, I'm telling you, everyone's kind of running to the finish line to get their pilots and their demonstrations completed, in which to prove out and validate the functionality and performance of their DLE materials and process lithium recovery and the quality of product produced in order to go to the market. Once you have your demonstration and proved out your process, as you're aware, that then you can go to the market, get funding, and that's where the full-scale commercialization occurs. Some people are at that full-scale commercialization. The majority of people right now are kind of in the pilot phase. So just kind of wanted to touch on where we were in that. And then on the left, it's sort of like breaking out the development of the DLE technologies by market segment. So could be oil field brines, or sometimes referred to petrolithium, or geothermal brines. Typically, those are termed as unconventional sources, deemed or defined by the lithium content is lower than something like a salar, which would be, you know, a couple of thousand, versus geothermal and oil field brines, which are going to be, can be low as 50 up to, let's say, 300. And of course, they are basically continental brines. So I'm only looking, just so you know, this is focused on brine, lithium recovery from brines. Of course, there's other sources such as clays or soft clays, a lot of development occurring with that, with different leachate and salt, I just read, and the other one, hard rock, which is the crushing and the roasting of materials. We're only focused on the lithium brines. So, you know, just an overview of where is the DLE material. Sometimes we hear, oh, you read an article or a press release about, oh, we validated our DLE process. A lot of the time, what we're focused, or what it's referencing, is just the DLE material itself, how well it's been able to absorb and extract the lithium from the brine source. So just on the process flow diagram or the process flow sheet, you know, where does the DLE fall? Well, just, you know, DLE falls just after the preliminary pretreatment. And then, of course, you have all these other unit processes. So this is what we're focusing on today. So when we take a look at the DLE technologies, as I said, we're only going to be focusing on sorbent and ion exchange materials, but there are a lot of other technologies out there that are not really the main players in the market space. But I think it's good to touch on them just to be familiar with them. So absorbents, as I said, is that material, the lithium chloride. Typically, it's going to go onto the materials. Ion exchange, I'm sure a lot of you are familiar with softeners, where an ion is going to come into into the resin material. I was going to say functional sites into the material, and it's called ion exchange because an ion of a lesser quality or value will kick off. So it could be lithium comes on and the sodium ion comes off. So it's an exchange. The good ones for the ones I don't want. Solvent extraction, that's out there, but you don't see a lot. One of the reasons is that lithium, the production of lithium from brines, or just lithium in general, is being viewed, I'm going to say, under a microscope and is being driven to be green, meaning low carbon footprint, good water footprint, low energy. There's no environmental impact to it. The solvent extraction, there's a challenge because of the chemistries used are aggressive and may not be environmentally friendly. Membrane separation processes is using sort of like a nanofiltration that the pore size, if I can call that, is think of the sieving, that the pore size is so small that the lithium ion is retained, or lithium chloride is retained, and all the other ones are rejected out. So developments, there's movement in that particular market space, such as nanotube technology that's coming up and developing. There's more developments, and I'm going to say progression in the nanofiltration technologies. I think DuPont will be coming out with a new membrane on that. So, and then electrochemical separation is using, think of it as electrolysis to force and separate the systems out, and sometimes called ion pumping. So we'll focus on absorbance and ion exchange, which pretty much dominate the market space. But the other ones, it's always good to know what the other technologies out there. So, why the demand? As I said, I'm not going to spend a lot of time in the market aspects to it, but batteries are expected to account for 95% of the lithium demand by 2030. Lithium's used in medical, it's used in ceramics and other materials, but the majority of the demand is coming for the electrical vehicles, which is by 2030, I think one of the estimates is going to be like 70% of the globe is going to have an electric vehicle. I'm pretty excited about that since I don't have one right now, but so that's where the batteries are coming from. Interesting is that there's not a lot of lithium in batteries, but because there's so many batteries, to give you an example, let's say like a Tesla car, the old the 18780 batteries, the smaller ones. I think there's about 17,000 batteries in a car pack. So that's a lot of batteries when you start multiplying the cars out. So lithium production, I mean, right now, the estimates, I think around 2022, it was like around 100,000 metric tons, let's say even 200,000 metric tons. I mean, by 2030, I mean, I can't even keep track of the stacks right now. So clearly the demand outstrips the supply, and via why everyone is going after that. Can the lithium gap be met? I think, with the technologies and the resources that you guys are finding out there, the answer is yes. Just as reference is that I believe that my own opinion that lithium brine is the one that's going to be focused on. It's easy to process. And when you take a look at environmental permits, I mean, you're looking at, 1 year to 2 years, depending on where you are, versus, let's say, a hard rock open pit mine that's going to be taking about 10 years before this thing's into production. So because you need to get the supply up as fast as possible, direct lithium extraction from brine is going to be the path. That's the solution. So starting the DLE selection process, every journey starts with the first step, but you need to know where you're starting from. So just a 50,000 foot overview is starting like I found it. How do I start this process? Well, first thing, you ask questions. Okay, the brine analysis and characterization. You need to understand, the dissolved metals, the organics, the contaminants, the silicas, other components in that. What's available not only in the brine, but when I'm taking a look at the DLE, there's other factors that you're aware. just on the physical location of the site, of the elevation, the ambient temperature, and then accessibility to the infrastructure, such as, is there a transmission line? Is there for energy? What's my end product, my carbon footprint? So all of these come into the main play when you first start off. So the previous webinar I kind of took a look at, there's a lot of questions. So it's good to build a decision tree or some type of, I'm going to say, fishbone process in which to guide you, because there are so many questions and variables. You need to put in a mechanism or a process in which to keep track, because you're not testing just, the onset of just one direct lithium extraction material or technology. You're probably going to be evaluating multiple. And the reason being is that the question I asked is that, does DLE work? Well, I'm going to give you a cryptic answer of maybe. And maybe means it because the brines are so unique, meaning that, every brine source has about 70% of the periodic table sitting in it. So it's a witch's brew of chemistries. So I'm going to take that, and they have different concentrations and different contaminants, and then I'm going to pump it through a DLE material. Well, different DLE materials have different specifications. So just because a DLE material works on this brine, it may not work on that brine. And that's what I mean by maybe. So there's a lot of analysis and a lot of research to do, and working with the DLE suppliers, that's critical in order to ascertain whether this is going to meet the requirements, and more so the performance. Performance being gauged as, what is the lithium recovery, or should the lithium extraction efficiency of the material? And then how, at the end, what is going to be my lithium recovery through my entire process? The lithium, the selection of the DLE material will also influence the downstream unit processes, as well as the upstream unit processes, meaning that DLE materials may require very tight filtration or and removal of contaminants. Others maybe are a little bit more robust. And then the downstream is going to dictate by, well, what's the concentration, and let's say the total dissolved solids of the eluate coming out when I deload the lithium from the material. So I won't belabor it. This webinar will be up and archived so you can review it. But as you can see, there's lots of questions, and I'm sure you're already there. So I kind of, when working with clients in that, I kind of stepping back and say, okay, let's take a 50,000 foot view at this. There's a lot of decisions, but let's start off with kind of the chunky monkey kind of components to it. It's what's the functionality is. Think of it as, first principles and work backwards. What am I trying to achieve? Meaning, what am I starting with? What's the process? What is being processed? Meaning, what's the characteristics or characterization of the brine? That's the first thing. I know that sounds like kind of a silly thing to make a statement, but it's curious how many times we work with clients, they do not have an analysis or a good semblance of what's in the brine. So, and that is so critical, as you're aware, is, if someone asking you how big's a box, well, I can't tell you unless I have dimensions. If you're asking if the DLE material is good, I can't tell you unless I have a full analysis of that material. Now, that being said, being appreciative of that, some people may have just finished their exploration, they haven't pumped up the brine yet, or they don't have enough brine for doing testing. So they may look towards doing synthesizing the brines. Just one comment: when you try to synthesize brines and put that through a DLE process, I'm going to say theoretical versus practical. That usually a synthesized brine is not going to duplicate the exact performance of a DLE material that you're going to see on live or real world. That being said, sometimes you have to synthesize brines just to kind of get the process moving forward. Lots of people can do that, but you need to have the formulations. The materials, property materials, we'll take a look at that. there's aluminum base, there's other different functional or materials used in the functionality of the resins, and those the material of construction will dictate the operating properties of the material. So that could be temperature, pH, and so on, alkalinity. Process, how is it being used? How am I going to be processing? How am I loading the brine? And how am I going to process it? Temperatures, and then lastly, the product. What am I expecting? What is the quality I'm trying? What is the finished product? Is it lithium chloride, lithium hydroxide, lithium carbonate? And what's the quality I'm trying to get out of this? Am I going to create a battery grade formulation and push that up, or maybe I'm just going to produce lithium chloride and I'm going to pass it over to someone else to do the processing, the refining. So starting with the process, the brine analysis, very generic, is that you want to start off with your dissolved metal analysis. I would say a complete dissolved metal analysis and a dissolved filtered metal analysis, so we can determine the metals that are in a colloidal or solid form versus dissolved. That helps because that's going to help dictate the type of pretreatment that you're going to require. The anions, typically this is by induced coupled plasma or mass spec. Anions is chromatography. Those are the type of analysis. The anions is critical because we want to get to an ion, balance out the ions. We want to have a balanced analysis. A lot of the times people will just kind of kick over a couple of them and it's not balanced. It's very difficult to do modeling if you don't have a balanced analysis. And what I will do, I'll make up stuff best of my abilities in order to balance it. But that is a critical thing. Organics, easy enough, but trace organics can have an extremely negative impact on DLE materials. So that's critical. Particle size and distribution, that also helps when you're taking a look at it. You're drilling, you're going to have you're going to have some residual fines in it, but on a long term, I want to know what I'm pumping up from the surface or from my brine reserve. And understanding particle size and distribution, as you can guess, that's going to play into the type of pre-treatment system you need. Can I use a multimedia depth filter that'll remove particles down to 4 or 5 microns, or do I need to start getting tighter, such as microfiltration, ultrafiltration, or maybe nanofiltration? That's going to kind of point you in the right direction. It's not going to give you the answer, but it'll point you in the right direction. pH of what am I starting with? Density is a critical one. Usually it's low, but that allows us to do modeling as well as calculations, hydraulic flows and resistance of your pumps. Silica, that's a critical one, and lots of other ones. So starting off, I can't emphasize, it's like building a house. You need to start off with a solid foundation. You need to have a really good analysis, well characterized. And if you have that, I'll tell you that your process or moving the needle forward on your DLE development is going to be quite quick, and you're going to be very confident in your modeling because of this. If you don't have all the pieces of the puzzle, it's kind of hard to see what the finished picture is. So again, I'll emphasize on the analysis. Well, having a complete analysis, I'm seeing it's quite long and lengthy, but there's a reason for that. And what you take a look at, if you take a look at the periodic table where everything is located in the groups, is what you'll find is that there are some substances that are easy to separate on the different DLE technologies than others. So easy ones are if I have for like lithium and nickel and so on, they are so far apart and have different characteristics that it's very easy to separate. So you can kind of guess where I'm going with this. So when you start getting elements that are close to their characteristics or physical properties, it becomes more difficult to separate those out. So this is why you see, and a lot of the analysis, if you haven't picked up, is that you'll say, okay, what's my lithium to magnesium ratio? What's my lithium to calcium ratio? Those ratios, why that's important to have, because it dictates the difficulty you're going to have with respect to separation. Now, some materials are better at separating and being more selective than other materials. But this is the reason why it's so critical to have an analysis and why you need to understand those ratios, because that DLE material is going to want, the DLE material supplier is going to want to know that, because some of them are better at separating lithium magnesium or either to be easier to be selective with some ratios than with other ratios. That's all. I won't belabor that. But this, when we talk about ratio, this is the reason what drives that, and this is why it's so important to have a good analysis. So when I say about the ratios, you have again, you've got ionic species that are competing against those reaction sites, or maybe displacing them, and that changes. Just so you know, is that when we talk about those ratios and the selectivity, well, selectivity can be influenced or changed by changing the characteristics of the actual fluid. What do I mean by that? Well, you can, if I change the pH, that may enhance or impede the performance of the exchange, different materials. Temperature is another one. Some DLE processes operate at very high temperatures because that aids. So again, different materials and selections, but this is the ratios or the materials we want to take a look at, and then taking a look at what those ratios are. And from that, you can kind of see, you know, from magnesium to calcium, sodium, and potassium ratios to lithium will give us an indication of just how well the material is selective, and how is that going to aid the lithium recovery from the materials. So these are important things or components to understand when you take a look, when you are relating that back to the efficiencies and the recoveries of the lithium. I know that's a lot to take in, but hey, if you took on the job of the DLE development, you're going to have a lot of late hours and a lot of information to comb through, as I'm sure you're aware. Interesting, just so you know, on the DLE side, I'm sure you find it as challenging as myself, is a couple of slides back when I indicated how many people are actually operating a DLE plant, or how many people are in a pilot phase. There's not a lot. And what I mean by that, there's not a lot of data points or data sets in which to prove out or validate a lot of the performance characteristics or performance ranges of these materials. So a lot of the times that the specifications that you're taking a look at is based off of laboratory testing or synthesized brines. So that is a very imperative question to ask your DLE material supplier, is where are these specifications coming from? Is this coming from real world, or is this coming from, forgive me for saying, best case or utopian laboratory conditions? Look, it's in development. It's challenging to have data points when you're starting a product up and so on. But I think that is a critical question to be asking the DLE suppliers, is where is this being used, and what is the data based on? So critical. I won't belabor that. I'm sure you have found that out already, and it is ripping the hair out of your head trying to disseminate all this information of what's real and maybe what might be fictitious. As you know, if there's a misstep in your DLE process, this could be hundreds of millions of dollars. So no pressure, but you understand the consequences of the wrong selection process or a misapplication on the wrong brine. So what are the properties and characteristics? Let's start off with the basics of the materials. This slide, there's going to be a lot of questions here in which to go through, but all of these on a cumulative basis, this is going to help you in your evaluation, in your weighting of the answers, in order to help you move towards the selection of a DLE material supplier. As I said, you're not really moving, maybe you are, but common is that you're going to be evaluating and selecting a couple of DLE suppliers in which to evaluate on your brine or send them samples. It's not just one. You pick the best, and then you're going to qualify and quantify their performances, and then whittle it down to a single selection. So part of that, the absorption capacity, start off with an easy one. What's the maximum amount of lithium that can be absorbed onto the DLE material? As I said, maybe the temperature needs to be changed, the pH, but really that's the key one. The amount of lithium you can pull off is really, at the end of it, that's the economic viability of your plant. This is going to have the biggest one on your preliminary economic assessment. So critical one. And this is why it's important to ask, where are you getting your data sets from? Is it from a lab or is it from a live stream? Selectivity is, again, it is when we talk about the ratios of magnesium and calcium, it's how selective is this material going to be in which to pull out the lithium. And again, because brines are very unique, it's a fingerprint. Every brine is different. The concentrations are different, the contaminants are different, so therefore the ratios are different. And this is what I mean by just because one DLE material works on one brine, it does not mean it's going to work on the other, because the ratios within the brines may be different, and the ratios are going to affect the selectivity of the lithium. So maybe you have to do some type of preconditioning. Maybe you have to soften the brine using, let's say, ion exchange or nanofiltration in order to get those ratios into the range in which the selectivity is going to increase and the absorption capacity is going to increase, if that makes sense. Separation efficiency, ratio of feed, it's just a ratio. I'm going to say, I'll skip over that. Recovery, the percentage, just a ratio of what people, you need a common benchmark in the industry. Ratio recovery is a good benchmark in which to evaluate one DLE material from another. Regeneration cycles, this is really interesting. As I said, that there is not, and this is a very important one because this comes into the life cycle cost of the materials. And like anything, when you start off with a brand new material, the performance is great. But of course, what you're interested in is how is this going to perform over time? And as with time, what you find is that, well, the cycles, I shouldn't say the cycles will drop, is that they are contaminants that may impede performance and reduce the cycles, excuse me, the cycles of materials. So some materials that you'll find, others I've read 2,000 cycles. An interesting point when you take a look at this is, in working with the DLE suppliers, is that when they tell you how many cycles, you really need to ask the questions, well, how did you calculate those cycles? Is it real world? Not a lot of people have that data, but then how did you do that projection? And I will point out one thing you should take a look at on the cycles, because microcontaminants will slowly load up on the materials. So over time, performance will go down. The cycles may go down, but that happens over time, over a couple of years. There's not a lot of data sets out there right now that have the cycles of performance over 10 years, because there is no DLE process that have been running for 10 years. So a lot of these are projections. So where I'm going with this is that one thing that you may want to consider is with the DLE provider is tell them to run the DLE materials, give you the performance, but then take that material. Some DLE providers like this and don't like it, and then have it pulverized and crushed and sent out for analysis and have those microcontaminants analyzed. Because if you see those microcontaminants, they're not going to go away. They're going to continue to load up on the material. So just kind of a quick, I'm going to say quick trick, take the material, crush it, send it out for analysis and see what type of microcontaminants have loaded up on it. Because after 10 years, or 5 years, 1 year, 5 years, it may be a lot. Cyclic stability is how well it's going to continue to perform after each cycle of regeneration. Is the performance being maintained, or do I see a decline in performance? Thermal stability, easy enough, is that if you're operating at a higher temperature, sometimes it's said is that you may want to elevate the temperature of the brine, which may aid increase the performance and aid in the recovery. But when you do that, I mean, just think if the higher the temperature I go, then the stability of the material may degrade. So something that operating at 20 degrees C, let's say gets 1,000, let's say 2,000 cycles. If I increase the temperature, the stability isn't there, and I may only get 1,000 cycles out of it. So that's a critical component. So evaluating that, if I play around with the temperature, well, maybe I can affect or impact what my life cycle costs are, meaning that I'm not going to have to replace the resin, at a higher. I'll replace the resin at a lower frequency. Environmental durability is what else is in the contaminants that could in the brine that could degrade it. Percent purity. Again, this comes back to the product selectivity. The extraction time is how long. It's an easy one. How long does it take to load up the lithium? Not the desorption, but how long does it take to load up the lithium? The faster I can load it, the quicker or the more lithium I can produce versus the longer. Another extraction time, just because of the kinetics, is going to be affected by the amount of contaminants, the ratios, but also how much lithium, the concentration of lithium within the brine. So think of that as the higher the concentration, the better the kinetics, because the lithium is bouncing and coming in contact with the material. So it's easier to extract. But if I only had, let's say, 2 lithium molecules in the same vessel, I might have to wait for that the lithium ion to kind of bump into it. So the higher the concentration, to a degree, the better the kinetics. That is one of the reasons that you, for geothermal or petrolithium brines, is there an opportunity in which to pre-concentrate the brines? If the TDS is low in the brines, then maybe there's an economic way of extracting water, concentrating up the brines, and in doing so, you also concentrate up the lithium content. That increased lithium content, again, will decrease extraction time, but also increase the efficiency of removals. And lastly, the specific energy consumption. How much energy is this going to take? Depending on where you are, in some areas that the cost of power or energy is going to be very high, others is very low. So that's all part of that, the production cost or the economic viability comes into play. So for the absorption and absorption ion exchange materials, really the associated cost is maybe I might have to heat up the brine a little bit to the temperature, or maybe the density of the fluid would be the pumping cost, different pumps efficiencies and so on. So as I said, for getting into kind of the meat and potato of it, I hope no one fell asleep, and that was good information. There's a lot of information to unpack on that slide. I apologize, but it was very important to go through that to get everyone on the same page of understanding. So on the two, as I said, you have absorption and absorption and ion exchange. One is that the lithium will be absorbed into the material and one will be absorbed onto the material. The different types of materials commonly that you'll take a look at on the ion exchange is there'll be a functional group on the ion exchange, and really it comes down to the lithium will go on and another ion will come off. So typically hydrogen is the exchange ion, and the source of that could be hydrochloric acid. So this is the material, the regenerant or reagents used in the regeneration of the materials. So it could be hydrochloric acid or sulfuric acid or H2SO4. That's the most common one. Depending on the cost differences between HCl and sulfuric acid is significant. However, one reagent may be on the long run in your calculations is that it may allow the material to perform better. Challenges with HCl versus H2SO4, it's HCl, is that you can only, the concentration of hydrochloric acid, you can only go so high. If you go too high, then there becomes a challenge of the pumping and handling, particularly if the gassing and getting pumps, not ceasing to pump, but stopping pump operations. So those are the two. There are lots of different suppliers of the ion exchange resin materials. It could be lilac. There's Geolith LiCap. There's Dow. Dow has a plethora of different materials. Again, this is just a assortment of the different ion exchange materials. There's lots more. Getting down to the absorption material and get into a little bit more unique. You kind of see that, here is I'm regenerating. I'm using typically hydrogen or maybe chloride for changing. Here we're getting down to a lot of different materials, and there's a lot of variabilities in this. So just quite quickly, the most common ones would be absorption materials that have been manufactured using an aluminum-based, magnesium-based, or titanium-based. I mean, those are probably the most common ones out there. Because of these materials, they have different specifications and operating requirements. And that could be on a pH, it could be on temperature, it could be, again, oxidants, that's a big one. So those are the type of materials, and they readily available. You can take a look at aramid symbol, FMC, which is really division Livent now. If you take a look at the ion exchange material and the absorption material, sometimes it's very difficult, or you cannot tell the differences between the two unless someone tells you. Resins are very, very small. This is at 500 nanometers here. So kind of indistinguishable. So make sure you label the resins and absorption materials if you're doing testing that, or you could mix them up very easily. So pros and cons, or I should say, sorry, the advantages and challenges of the different materials. So absorption materials are kind of unique versus the ion exchange, is that absorption materials is that I can use water in which to basically unload or desorb or remove elute the lithium off the material. So, of course, water being a lot more environmentally friendly, that's great. There's a lot of processes or ways that then we can take that water, clean it up, and reuse it back in the process. And particularly when you take a look at in South America, where that's where the majority of the lithium reserves are located. And because of the geographic location, that in that area, like water scarcity is critical and is a #1 driver of getting your lithium project approved as it goes through the environmental review and evaluation process. The water footprint is going to be a huge one. So if you can say, hey, I'm going to use water and I'm going to reuse it, that's really going to help and support getting the environmental permits that you're looking for. if you're not reusing the water, then that's going to be a real challenge getting your project through. So there is the other component, because I'm using water, it just means that then I'm not going to have waste reagents, which I'm going to have to get rid of later on. So different materials, as I said, could be aluminum-based, magnesium-based, titanium-based for absorption materials. The efficiency depends on the supplier. You're looking anywhere from, I'm going to say, 80% all the way up. Some have even posted 100% efficiency. Again, posted. I haven't seen the data on that, but those are the range that you're seeing. The other aspect to absorption materials is that you typically have to operate the brines or the loading at a higher temperature. Now, that may not be a problem if you're doing geothermal brines, that they're already at a high temperature. In fact, the challenge might be you have to cool it down. So that's great. I mean, so absorption material, if you're saying, hey, I already have an elevated temperature in my brine, I won't have to heat it. Well, absorption material is something to take a look at right away, because that's going to help improve the recovery rate. So the other challenge is that even though it can operate at a higher temp, it's as I said, the highly selective, that the eluate is lower than ion exchange. So ion exchange materials, different materials that you can use. There's lots out there. They have, I'm going to say, very high selectivity. It's a well understood technology, and it is a robust material. I mean, on the thermal stability, on the porosity, and so on, it's well understood. There's years and years and years of R&D and development in developing these materials. So very, very solid. Challenges, of course, is that you're going to have to use a regenerant. So, as I said, sulfuric acid or hydrochloric, and that's going to lead to waste. Sometimes you can regenerate, sometimes you don't. So one of the components in these areas is that, well, if I generate waste, how am I going to get rid of it? And then what's the volume that I have to get rid of? Some areas that very easy, you can get rid of it. Other ones may have a lot of restrictions. I won't talk about the solvent extractions, the membranes, but these are the key ones. Where are they in the development? I mean, a lot of on both the absorption and ion exchange, these are mature technologies, so they are ready for the market, and with the majority of them being commercialized, as I said. And some of them have already, and this is why I say ask the question, some of them are already run pilots, and they have data on live brine streams. So they've done the pilot, they've done the demonstration plants. That's, as I said, critical, and those are the ones that have, I'm going to say, surpassed the other people that are still working on the bench scale. So, just a quick thing on the absorption materials. As I said, higher temps, and one of the advantages is that you can use water to elute the lithium off. So, one of the key things, particularly in South America, or water stressed areas, I'll just term it as that, is that there's a displacement cycle. What I mean by that is that you load the brine into the columns of the reaction vessel, or the loading vessel, I should say. And then prior to eluting the lithium off, particularly on absorption material, what you want to do is I want to get rid of any residual brines in this. So I will go through a displacement cycle. So I will pump water into this, or diluted lithium chloride, and on a plug flow, I'll push the brine out of the column and prepare the materials to be eluted. So during that process, I'm pumping out, as I'm putting water into this and I'm pumping it out, I've got diluted brine solution, which is the opportunity that it's a lower TDS, I can recover that water. So I'm just saying on the absorption, material process during the displacement, you could recover that water. That's not the case in an ion exchange for obvious reasons, since you're not using water for displacement. So something to take a look at, particularly in water stressed areas, that you can recover that water. So in taking a look at the DLE materials, the other one is that, well, how am I going to load the brine? How am I going to interact the brine with the materials? Most is that you'll find that it'll be a resin vessel or maybe even a cartridge. But the other things to keep in mind that you can load up is that I've seen that use of a static mixer is that where you're actually fluidizing the resin material, and you're going through a static mixer where it intimately contacts the brine. So rather than just loading it up into a vessel static and then putting the brine into it and letting it soak in, what people are trying to do is take a look at, or working on, is that, can I do this? Can I create a continuous online process? Or maybe this is the way that I'm going to mix the materials with the brine. And in doing so, if I have a cartridge, and as you can guess, is that then I have to force the brine through the liquid. I could have short circuiting within, if there's or channeling within the material. Let's say the materials aren't packed evenly, and I've got channels that kind of run through the side, so I can have short circuiting of the brine going through the resin material. So how that resin is packed and configured into the vessels is critical, because I can get bypassing and I can get reduced performance from that. This static mixer, the intent is that I'm going to flow it through, and because I'm fluidizing the material, you can think that that bead is coming into intimate contact and it's rotating around and it's being hit by brine from all sides. So in theory, it's good. I haven't seen a lot of data on that, but I think in theory, I think it's a good concept, and I'm looking forward to read more materials on that, particularly on the efficiencies of this versus this or this. Another component, this is kind of the a mixing or loading tank, kind of the same thing of this a static mixer, but a different take. Standard lithium, this is kind of what they're using in their process, where the resin's in the tank, they load the brine, they mix it up, and then they pump the fluidize or the slurry over to another vessel to be eluting. So when you're looking at your DLE process, the other thing is, well, how is the brine going to be loaded onto the material? Some people, a cartridge is quite interesting, because when you take a look at the other aspect of your DLE is the flexibility in the scalability of the process. Some people start, well, I'm going to be 500 cubic meters a day, then I'm going to scale to 1,000, and then maybe 2,000. So I've got my process. Well, how easy is it going to be to upgrade or modify that plant? So, I've got to add different things. Cartridges is a kind of a neat way of doing it, as well as just loading at the vessel. But that's something to take in consideration. You're not talking about one or two cartridges in these large plants. You're talking about thousands of cartridges. So something to take into consideration. And of course, everything takes up space. So the other component is that when you're looking at the end product, well, what am I trying to achieve? Is it lithium chloride, lithium carbonate, lithium hydroxide? You take a look at the market between the price differences between lithium carbonate, lithium hydroxide. There is a difference, but in trying to disseminate, is there advantage of producing one product over another? I have not been able to conclusively say that, yes, all plants should be lithium carbonate or lithium hydroxide. There's still both command good value. both can be used and converted within the actually conversion factories. So there's nothing, I haven't seen any trend towards one product to the other. The other one is lithium chloride. It's that when you elute this, you have your DLE material and you elute, lithium chloride comes off. So one aspect, it could be, well, I'm going to clean this up, take out the contaminants, but I'm going to be taking the lithium chloride. I'm not going to be doing the conversion, polishing and conversion. I'm just going to send that out to a converter. And they have expertise and specialty and their equipment on that. So rather than me building my process for polishing, continue to do the concentrate, I should say polishing and then conversion, I'm just going to send it out to someone else. So that's another thing when taking a look at your DLE process is, what is the end product? If I'm going to have something converted, then, maybe the selectivity or maybe the contaminants in the elute, it's not going to be a big issue for me because someone else is going to be handling them. So just saying those are some of the questions to take a look at and some of the questions I have for our clients. So I thought we'd take a look at, just so just as we get into some time here, just the different types of technologies, or I should say DLE providers, as I'm sure that if you're not at that stage and haven't selected someone as of yet, then you may be interested on, who's out there. So just as an example is Geolith. I mean, they're out of France. They have a certain, it's ion exchange material. Their specifications are 90% to 100. And they have a couple of pilot plants and actually data sets which they have used in order to put out their specifications. So some people to talk to. E3 Lithium out of Canada is, this is a proprietary material. I don't know if they're selling their sorbent yet, but maybe later on. So they've got a lot of data on that. And again, they're using an ion exchange, but it's proprietary. So I apologize, I don't have a lot of information on that. DuPont, DuPont has been around. They've been doing DLE extraction since I think 1970s. May not be on lithium, but other materials. You can also take a look at, prior to DuPont, be Rowan Haas or Dow. So lots and lots of experience. They have a very large portfolio of materials, sorbent as well as ion exchange materials to select from. So there is not one I listed down. So I'm going to say that if you're interested in that, best just to call them directly. Taking a look at, I'm going to say there's Linux technology. I didn't put this into the handling, but an interesting one is the pack bed technology. So we talked about, cartridges, ion exchange vessels, static mixers, a mixing tank. Kind of a different. This is kind of unique. They're out of Ontario, Canada. This is the old Ecotech technology, which is packed bed. So basically, there's no freeboard. It is a literally packed vessel of the resin, and it's using the Linux material, which was actually acquired from Chemionics, if you remember those days. So the absorption material is around 95%. That's what they listed at. Another company's added Adionics. As you can guess, there is lots and lots of DLE material suppliers out there. Again, I'm just giving you familiarity of them. There's difference. We talked about the different materials. They operate their process at an elevated temperature. So, they are involved in geothermal brines because of that elevated. They are 75 to 90 degrees, and because it's absorption material, they're using water to strip off the lithium. Lilac, that's out of California, Bill Gates Foundation. They have a patented ion exchange resin. I apologize, I couldn't get a lot of information on that. but it is ion exchange. They use hydrochloric acid, not sulfuric. They feel that the performance is better with that, and the material is mixed in brine tanks. They have, I should say, they also have operating pilots and data. Samo Nanotech, this is a little bit different. I just thought I'd put this in. They're based out of Canada. There's their process is a little bit different. It's absorption and nanofiltration, and the difference approach they have taken and they feel is more advantageous is that they use nanofiltration, or think of nanotubes. So they're actually taking the absorbent material, they elute it, and then what they do is they pass it through nanotube filters, which have been designed specifically to be selective on the lithium. So it's not just one material, it is a process that they've put together for the elution and refinement of the lithium. So a little bit of a different take on it using nanotubes. Another one is Iliad. This is a little bit different approach. What they are doing is they've not only taken a look at the DLE material, but the function of the material. And kind of mentioned before, I said the containment is there's a cartridge, and what they do is they've built a cartridge. And unique, the way that this works is that it is think of it as a round table, and the brine comes in and it basically fills and processes each one of these cartridges. So it works on a continuous basis. So a little bit different. So just like Summit Nanotech not only looked at the absorbent material, but they're looking at, well, the process. How do you simplify and how do you create a more efficient process? So this is kind of what Energy Source has taken a look at, is this cartridge type of approach of how to do the DLE elute. So as I say, getting into it, is that when you take a look at the DLE processes, there's a lot to take in. Starting off with just in summary, is that you need to start off with the analysis. That's the foundation in which everything is going to be modeled and built from. It's critical to have a good characterization. Two is understanding, once I have the analysis of what are the characteristics of the brine, is it going to be an elevated temperature, the contaminants that I need to deal with, and so on. The DLE material, the performance, as we said, is this is a challenging one because there's not a lot of data sets out there. So I'm going to say it's critical that you work with a DLE provider. If you cannot provide them a live sample of brine, then work with them to try to synthesize a brine as close as possible to begin the evaluation. I will say again, the synthesis is never the same as the real live brine, but sometimes that's what you need to do to move the needle forward. And then lastly, it's that how is this going to be, processed? How's it going to be loaded and deloaded? And those are really the overviews of the material selection process. Again, the key takeaway from this is that you need to really take a look at what when you do the analysis of what those ratios are of the lithium to, I'm going to say, to contaminants, magnesium, calcium, and so on, because that's a good starting point to talk to your DLE material supplier, because those ratios is what's going to affect the performance of the DLE materials. And once you get that figured out and solved, then you can start taking a look at the concentration, the polishing, and the conversion steps. So with that is the end of the presentation. I greatly appreciate you attending. I really hope this provides you with a little bit of insight. The challenge that you have is the information within this space, there's not a lot. So it really rests on your shoulders to do a lot of the legwork. I'm going to say the heavy lifting. But I emphasize, work with your DLE provider, and you know, a lot of them are good and can help guide you and give you a clear path down, and get you to your finished goal, which is a piloting demonstration and of course commercialization. With that, thank you very much. I really appreciate it. And that is the end of our presentation.
Thank you so much, Grant. I have opened the Q&A, but no questions yet. As we said at the beginning, the webinar will be available on our YouTube channel as well as our website, so you can always refer back to it there.
One thing that I found that to help speed up the development of the DLE is that once you have, I'm going to say, selected your DLE provider, and they have developed, I'm going to say, the operating practices or the standard operating practices, the SOP. What we've been doing is that I'm going to say, partner with the client, the DLE provider, and ourselves. We focus on concentration. And what I mean by that is by working collectively and having the ability that the DLE provider sends us their cartridge DLE material, then we can take the brine, run it through, create the eluate based off their SOP, and then go through the next step of concentration. What does that mean, or what's the benefit of that? There's a lot of time where, you know, you send a sample, brine sample to the DLE, they run it through, they get an eluate, then the client sends the eluate over to us, and then we send, you know, the eluate over to, so it becomes a lot of time because you're not talking one sample, you're talking lots of samples. The time required to ship this stuff back and forth can add up to, you know, weeks, if not months. By eliminating that, by working collectively together, by working with the DLE, and I'm going to say the post-DLE, the concentrating side, and working together, you have the ability to understand and optimize that system. So you can try something, see the reaction, and then within a minute, well, let's try something else. So for cause and effect, action, reaction. So it speeds up the process when you work collectively together. Any questions? Great.
Nothing yet.
Okay. Well, thank you very much, everyone. And hey, if you've got time, Thursday, there's another presentation we're going through, and this is on using solar thermal in your DLE process of how to reduce your energy costs and your CO2 footprint. So thank you.
Thank you very much.
Have a wonderful day. Cheers.
Bye.